Okay, so welcome to this fifth lecture of complex analysis course. So today we are going to start a new topic completely. So we're now finished with the power series and all these things, and also the multi-valued elementary functions that we have now studied, the branch cuts and so on. So now we will start with talking today about conformal maps. Okay, and we will also try to talk about Möbius transforms today, given that we have the time. So why are we going to talk about conformal maps? So let me remind you, so let's go back a few lectures, and we talked about holomorphic maps, and we said that holomorphic maps, they satisfy these Cauchy-Riemann equations. So this is a sort of analytic way that we can test if a function is holomorphic by computing these partial derivatives and seeing if they are equal in the appropriate way, according to the Cauchy-Riemann equations. But it's not something that says very much geometrically about what it means to be holomorphic. Okay, it satisfies some conditions on the partials, but what does it mean? So what do the Cauchy-Riemann equations mean? So let's see. So we're now going to give a sort of geometric interpretation of the Cauchy-Riemann equations. Okay, and so I want to start with this motivational example. Which is a kind of nice remark. So let's say that f is a function u plus iv. Okay, and we view it as a function, so viewed as a function from R2 to R2. Because of course, topologically again, we can identify C with R2. So you remember we can do this. So this means that U and V are functions from R2 to R, or equivalently from a subset maybe of R2 into R. And this would then be a function from a subset, the same subset of R2 into R2. Okay, and these are open subsets. Open subsets. Okay, and then what we can do is we can look at the total derivative. So when you have a real valued function that is differentiable, so assume that this is differentiable. Okay. As a function, viewed as a function from R2 to R2. Okay, so differentiable now not in the complex sense, but as a function from R2 to R2. So the partials exist. Then we can consider the total. So I don't know how much you actually remember of these. I mean, in multivariable calculus, you don't necessarily study super much about functions from R2 to R2. It's mostly like Rn to R, or something like that. But when you have functions from Rn to Rm, so when you have this total derivative, which you will remember is a matrix, right? Sometimes called the Jacobian. Sometimes you also call its determinant the Jacobian matrix. So you have the total derivative, so let me call it J for Jacobian, which is partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y. Okay, and now what does it mean to satisfy the Cauchy-Riemann equations? So now, if we satisfy the Cauchy-Riemann, so if Cauchy-Riemann holds, then of course we can rewrite this in some appropriate way. So what were the Cauchy-Riemann equations? Can you remember? So let us keep the first row. So let's write it partial u, partial x, partial u, partial y. And then partial v, partial x, what was it equal to according to Cauchy-Riemann? Exactly, so minus partial u, partial y. And then partial v, partial y was equal to partial u, partial x. Okay, so just to see it more clearly, this is equal to a matrix of the following form. Okay, so really, so the total derivative is this map from R2, so it's a linear map from R2, which sends this vector xy in R2 to this AB minus BA times xy. And geometrically, what does this do? So this is the sort of miracle. So any holomorphic function satisfies the Cauchy-Riemann equation, so its total derivative viewed as a real function must be of this form. And what does such a matrix do? Okay, so first of all, so let's say for simplicity that B is 0, then it's just A times the identity matrix, then it's just rescaling, right? So yeah, quantity of scaling. And if A was 0, then it would be minus BB, then it would be a rotation, exactly, so it would be a rotation. And so this kind of matrix is a composition of rotation and scaling, okay? So this means that, so this is composition of rotation and scaling, okay? So this in particular has, so then this connects with this notion of conformality. So conformal means to preserve, so conformal map means a map that preserves angles and orientation locally. Okay, and this will actually mean precisely this. So I will now give a formal definition of conformality, but sort of the way to think about it, the informal one, without giving all the precise statements, is this, that the conformal map is something that preserves angles and orientations. So of course the simplest examples of conformal maps would be exactly a scaling or a rotation. These very clearly preserves angles and orientation, but also much more complicated things can actually be conformal. And in fact, what I'm saying is that every holomorphic map is conformal, which means that, so it's not locally conformal, it's conformal, which means it'll be locally preserve the angles and orientation, which is kind of a miracle. So I mean, so something, for example, that is not conformal, so not conformal, example, what would that be? So if you just think about the examples of non-holomorphic functions that we have seen. So I like, for example, this one, f of x plus iy maps to x. So then it means that if you take some curve here, so you take this imaginary axis and this real axis. So this imaginary axis will sort of here where it's a 90-degree angle, but it will be collapsed onto the real axis. So angles are not at all preserved, you see? And so not only will holomorphic maps in fact be conformal, but assuming that you have a real differentiable function whose partials, so using some appropriate condition, just as we did before when we said Cauchy-Riemann equations are roughly equivalent to being holomorphic, assuming regularity. So if you assume the same regularity, so that the partials exist and are continuous, then actually conformal maps are holomorphic. So this is geometrically what it means to be holomorphic. Okay, this was a non-example. So you can see it's clearly not conformal, but it is, its partials exist and are continuous, so it cannot be holomorphic also for this reason. Okay, so let's now give a formal definition of a conformal map. Let's start the formal discussion. So, let's see. So formal definition. Okay, so a map F from A to C, where this is an open set, okay, as usual, of C, is conformal if the following three conditions hold. So first, so as a map, F from A, so now viewed as something in R2. So this is clear, right, that I make these identifications without saying anything special. So viewed as a set, so a subset of A is trivially identified with a subset of R2. So viewed as a map from R2 to R2, it should be real differentiable. Okay? So this means that this Jacobian, this matrix of partial derivatives exists in particular. Okay? And F preserves angles of intersection between smooth curves. So now for just 1 second it becomes a little bit differential geometric. So you will have this course next semester, differential geometry, where you will become experts in dealing with all these smooth curves and tangent vectors and all these things. So from now on, I will just try to explain to you best you can with a background. So it preserves angles between smooth curves. So what is a smooth curve? So a smooth curve is a map, so parameterized by R or some interval in R, to gamma of t, which is gamma 1 of t plus I gamma 2 of t, where these are smooth functions of t. So you get some curve, gamma of t. So this is gamma of 0, and then you have gamma of t here, and you have a curve like this. And an important thing to emphasize, so we will get back into this in more detail when we integrate later, but a curve is a map. So a curve is not the image, but it's a map. So for example, a curve could have this image, but included in the data is also the parameterization and the fact that I start here and I go in this direction, for example. And formally it's a different curve if I start here and go in the other direction. So gamma of, let's say, minus t, so let's say this is gamma of 0 and this is gamma of 1. So if I take gamma of minus t, it's the same curve going in the other direction, and this is formally a different curve. So a curve is a map. This is a very standard idea in mathematics, in differential geometry, but maybe you have not seen this idea yet, so I want to emphasize this. That the curve is not the thing I draw, it's the map that parameterizes the thing. But this is differential geometry, okay? So what does it mean now that the angle of intersection between smooth curves, sorry, now I wrote curves twice, between smooth curves is preserved. So what does this mean? So it means that we start in a point here, and then we take two curves. So we take gamma and gamma tilde, and then we take tangent vectors. So even though you may not know exactly rigorously how this is done, I think you have all done something like this in your lives. So we have the tangent vectors of these two curves. So they go in the direction that these curves start exactly in this point, 0, okay? And then there is an angle between these vectors, okay? And this angle here, let's call it theta, this angle is preserved. So when I map these curves onto something entirely different, let's say I map it onto something that looks like this, then this angle here should still be preserved, and this is f of gamma of t, and this is f of gamma tilde of t. Okay, so under some map I can look at the image of curves, and maybe something happened, so they went from this to this, but this angle should still always be preserved, whichever smooth curves I take. So this is just an example. Okay, what does this mean if we write it down? So let's take these tangent vectors and let's call them. Yes, question?
Should we take the angle between f of gamma and f of gamma tilde clockwise or counterclockwise as it is in the domain?
Yeah, so I will come to this. Yeah, so orientation is important, as you say. So it's important that the angle is taken in the same way. So for example,
so here it is different.
So here maybe I took it in the wrong way. Okay, let's see. So here,
you start.
Yeah, exactly. So so this will be the third point in my definition. So far I was just explaining angles, but the third point will be that you also have to preserve the orientation, which would mean, indeed, as you point out, that gamma tilde should be the upper one. So we'll explain what that means. But first, let's say that this is alpha and this is beta. These are the tangent vectors. Okay. So alpha, beta tangent vectors Then what is the angle between these vectors? Well, now we are working in sort of differential geometric setting, so you remember that really for us the angle would mean that the scalar product of alpha and beta over the norm of alpha and the norm of beta is preserved. Okay? So this is what it means. So this is sort of the angle. This is what we identify with the angle. Because you remember there's this, so you remember that alpha beta is equal to, I believe this is the formula, so alpha and beta, something like this. You remember? So, of course, if this ratio between this and this is preserved, it means that the cosine of theta is preserved. And this is what we will sort of call preserving the angle. Okay? In this sense. So you want to preserve this. And so what does it mean? So it means that if you take the tangent vectors of f of gamma tilde and so here you have alpha and beta and here you have some other vectors, and which ones are these? Well, you can't express them in a simple way. So it means that so the tangent vectors at of f of gamma of t and f of gamma tilde of t at t equals 0. So they are given by multiplication by J, which is this matrix, this total derivative matrix. Partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y. Okay? So it means that instead you look at this J times alpha, J times beta over so this becomes the condition. Okay. So now, as I said, this is not a course in differential geometry, so therefore I am sort of not going into the depths of all these things. So I will just say that this is what it means, and I think you can all understand this by thinking back to your multivariable calculus course or something like that. You think about it for a few minutes, and you can realize that the tangent vectors here are given, the angle here is given by this. And so preserving this angle means that this angle, which is this, is equal to this angle, which is this thing. Or really the arc cosine of this thing, but preserving, having this equality is equivalent to the other equality. So this is what it means, the second condition. Okay, and then we look at the third condition. Where did I put this? It's here. Okay, and we look at the third condition, which is the following, that f, so this is what was pointed out, that it has to preserve orientation. So f preserves also orientation. Okay, preserves orientation. And this means that the determinant of this matrix is positive. So this is how you can test this in practice. So an example of something. So what does it mean to preserve orientation? So let me draw a picture. So this is what we said earlier. So here we have alpha. Here we have beta. And this is the angle. So now if we take an example of something which does not preserve orientation, to try and explain it this way, it would be something like the conjugate. So let's say we look at z mapped to z bar. So then alpha would map to alpha bar, okay, alpha bar, and beta would map to, sorry, it's not the greatest drawing in the world, but it maps to beta bar, which is this. And now this angle here is still preserved, okay? So angle theta is preserved under this map. Z goes to Z bar, but is the orientation preserved? Well, it's not, because I sort of flipped it, okay? And this changes the orientation. So preserving the orientation means you cannot do such a flip. So, if one is to the left of the other or something, it still has to be to the left of the other. So you see here alpha is to the left of theta, whereas here alpha bar is to the right of theta bar. In whichever way you want to say it. So here there is a flip going on. So orientation is not preserved. Okay, and this means that this is what we call anti-conformal. Okay, so this is an anti-conformal map. So anti-conformal means that you satisfy the first two conditions, but not the third. So you switch orientation, but you still preserve angles in your real differential. Okay, and all these anti-conformal maps, they are all of the form, of a very simple form. So exercise, they are all of the form Z goes to F of Z bar for F conformal. Okay, so I hope you can see what I write in this remark. So this is an example of something which is not, which preserves angles, but which does not preserve orientation. So it's close to being conformal, and really in some sense, it does most of the things that you want the conformal map to do. So it's close to being conformal, but we call it anti-conformal, satisfying the first two conditions, but not the third. And all of these functions, you can see as an exercise that this is of this form. Z goes to F of Z bar. So really, if we are interested in studying anti-conformal maps, if we understood all the conformal maps, then we also understand anti-conformal maps and vice versa, because we just take the conjugate of everything. Okay, so really studying anti-conformal maps and studying conformal maps are two sides of the same coin. So really we can forget about these and we just study the conformal ones. And these ones will come sort of for free. So now, I will prove an important theorem about conformal maps and holomorphic functions, showing that holomorphic functions are conformal and conformal maps with some regularity condition are holomorphic. But first we have some good question about the definition before I go on. Okay. Very good. So now, the miracle about this is the following theorem. Okay, so the main theorem.
The orientation is a global notion or local?
It really means. So this is a local notion. So you're looking at the intersection between curves and how it maps. So if you flip like this locally. So this is
anti-conformal means that
that you reverse orientation, but you keep the angles. Yeah.
In every point.
Yeah, exactly. So like Z to Z bar. This is the prime example of this. So at every point, if you take two curves, you will flip them over. You will preserve the angles, but you will flip the orientation anyway. Okay, so theorem. So suppose this is conformal in this open set. So this means again that UV goes from R, so from A to the subset of R2 into R. And then the Cauchy-Riemann equations hold. Okay. So now actually, so to save time, I will stop writing like this, partial U, partial X, because I will write it a lot, and I will write U sub X. This means partial U, partial X, okay? Uy Vx, Vy. Oh, sorry. This is not what I wanted to write here, but Ux equals Vy and Uy is equal to minus Vx. Okay? So I write it this way to save time. So this Cauchy-Riemann equations hold, and conversely, so if UV satisfies Cauchy-Riemann and Ux, Vx, Uy, Vy exist and are continuous, then F equals U plus IV is conformal. Okay, so you see, so in particular this means that if you assume, if you have a function, if you restrict your attention to functions that are sufficiently regular, so you restrict to real differentiable functions where all these partials exist and we are continuous, so most functions that you usually consider are like this, then indeed conformal is equivalent to satisfying Cauchy-Riemann, which is under those conditions equivalent to being holomorphic. Okay? So for sufficiently nice functions, being holomorphic, being conformal, and satisfying Cauchy-Riemann equations is the same thing. But you need to be careful if the real differentiable function has very low regularity. So if these partials are, for example, not continuous, then you have to be careful. Okay? So this means that, so I mark for regular enough functions, and I'm saying regular enough because you remember I gave you this paper on Cauchy-Riemann and the optimal conditions, right? So there are perhaps some subtleties on how you can push this to the optimal condition. But for regular enough functions, conformal is equivalent to F holomorphic, which is equivalent to Cauchy-Riemann equations satisfied. Okay.
What is the relation between conformal and holomorphic? If the condition this the partial derivatives exist and continuous.
Yeah. So then.
Not hold.
Yes. Sorry. If they are not continuous.
If they might be not continuous. So is there a relation between a function being holomorphic and conformal?
Yeah. So holomorphic functions are conformal. So as a result, but conformal functions might not be holomorphic, I believe, if it's not sufficiently regular. I think. I'm actually not sure of this, of how it goes the other way. But for sure, passing through the Cauchy-Riemann equations at least is not true.
But the theorem is saying us if the F is conformal, then it is satisfies only Cauchy-Riemann equation, but it cannot be holomorphic.
Yeah, so I mean, so the thing is that it is possible that holomorphic and conformal is completely equivalent always, but it's just the relation with Cauchy-Riemann equations that fails. This is why I'm hesitating. You see?
In this case,
So it could be that Cauchy-Riemann does not necessarily imply holomorphic, but conformal.
But if the map is conformal,
Yeah.
then the matrix of the differential has the form A, B minus A, B. So if it's conformal,
But that is if
then
it's
then the Cauchy-Riemann equations are satisfied automatically.
yeah, if it's conformal and has some regularity condition.
Yeah.
So you see.
Yeah.
So at least we need this matrix to exist.
Yeah.
Otherwise, we cannot talk about it. And I mean, it is a priori conceivable to me that you could have some conformal map where this matrix is just not defined, you see. So this is why I'm reluctant to say yes, because I'm not sure if there is some such thing, you see. But in general, you should think of these as equivalent things, unless there is some very special thing going on, okay? Okay, so let's see if we can prove this. So proof. Okay, so first we suppose that F is conformal So yeah, so we suppose it's conformal and we want to show that the Cauchy-Riemann equations hold. So all we know now is that we have, okay, so it's conformal and by definition, actually, so conformal by definition means it has to be regular enough to have these equations. This is what I just wrote. Yeah. Okay, so conformal. So by definition, so we can write down this matrix. Okay. All right. So this was part of the definition, and then I can look at the column vectors of this matrix. So I can look at this is alpha, and this is beta. Okay. So I look at alpha is ux dx, beta defined as uy dy. And then I note that, so by definition, conformal map preserves angles. Okay? So, by definition, F preserves angles. So in particular, if we look at this map, this J here, which is a matrix, acting on 1, 0, this, so 1, 0, let's put it this way, so 1, 0 is orthogonal to 0, 1. Yes. So it's orthogonal to 0, 1. So this implies, by this map being conformal, that J times 0, 1 is still orthogonal to J0, 1. So J10 is still orthogonal to J01. So I have applied this matrix. So this is what it means if you remember what I explained about the second condition. But really, preserving angles, so what you do is you multiply by this J. So this is the definition, how the definition works, the conformality. But what is this? This thing here. So if I take this J here and I apply it to 1, 0. So this is alpha, and this is beta, exactly. So alpha is orthogonal to beta in this matrix. I take a column vector, so alpha is orthogonal to beta. So moreover, so this is the first thing. The second thing is that I can look at 1, 1. Okay, so I look at this vector, 1, 1, which is orthogonal to 1, minus 1. Okay, so these two are orthogonal, and this means that J11 is orthogonal to J1 minus 1. But now what is this? J11 expressed in alpha beta? It is clear how we get this, right? So you remember. So this is alpha plus beta, and this is alpha minus beta. Okay, so alpha minus beta and alpha plus beta are orthogonal. So what does it mean now to be orthogonal? So in terms of the scalar product, it means that the scalar product is 0. So now let's see what we get from this. So we get that 0 is the scalar product of alpha plus beta and alpha minus beta. But what is this? This is equal to the scalar product of alpha and alpha plus the scalar product of beta. Minus scalar product of beta and beta. Okay? Yeah. And so this is equal to the norm of alpha squared minus the norm of beta. Okay. Okay? And so what this means is that, so this is equal to 0. So we get that the norm of alpha, or the absolute value of alpha, is equal to the absolute value of beta. Okay. Now I wrote it like a norm, so it was a norm space, but it doesn't matter. Okay. So they are of the same length. Okay, so what does this mean? Now we have to remember, so alpha beta, so alpha is orthogonal to beta, and they have the same length. So what does this mean? You remember maybe this picture, but so now if this vector is AB, then what are the coordinates for these vectors? Right, so here if I had, it's actually clearer if I draw it a bit closer. So like so, okay. So now this was A and this was B. And this one will actually be, so here we will have minus B and here we will have A. Okay, and here in the same thing we will have here minus A and this will be here B. Okay, so this means that this, now I'm just writing down alpha, so it is equal to plus minus Vy minus Ui. So that's equal to this, using this kind of picture. Is that clear? No? Sorry? Yeah, so this is what should hold. So here, so this one is equal to minus BA, or here we have what? We have B minus A. So it is equal to plus minus so what did I have?
Yeah, that's it.
Is it correct? I got confused. Okay. Okay, good. Sometimes when you stand at the blackboard you see nothing anymore. So, okay. You're happy with this? I read it last time. I mean, it should be true. I checked it yesterday. So, okay. And it's for exactly this reason. So then, what does this mean? So it means now if we look at the determinant of J, okay, then it is equal to plus minus, so instead of ux, so I put ux, uy, but then I put, instead of vx, I can put minus ui, okay, and instead of vy, I can put ux, okay? And the plus minus here, you can see that it checks out. So this is equal to plus minus ux squared plus uy squared. Okay? But this has to be positive because f is conformal. Sorry? Because it preserves orientation. So because f was assumed to preserve orientation, it means that the determinant of J has to be positive. Remember, this was the first condition. So then we know its condition, so we know it has to be plus, exactly. And the fact that it is plus corresponds to having plus here. Okay? So you can go and check this if you want to use pen and paper to see it. But if you write that, so it means there has to be plus here. So this means that, in fact, S conformal we have equality so this implies that this vector ux dx is equal to plus vy minus uy. Okay, so this means exactly this. And this is Cauchy-Riemann rewritten in some way. Hopefully you recognize. So then Cauchy-Riemann is satisfied. Okay, so that was one part. Conversely, the other part is easier. So if CR is satisfied, if Cauchy-Riemann equations are satisfied, and it's differentiable, you know, we have these regularity conditions, then we can again look at this matrix, and then this is equal to, so we have these things, so it's equal to ux, I will keep ux uy, and then I will say that vx is equal to minus uy, and vy is equal to ux. Okay, and then I can do the same thing. Okay, so first of all, if we look at now, so we call these alpha and beta, okay? Alpha and beta are these column vectors. So then alpha and beta is equal to, so it's equal to ux, ui, minus ui, ux, okay? So now I'm taking the scalar product of this vector with this vector, okay? And this is equal to 0. So the scalar product of the column vectors in this matrix is 0. And if you remember, what does this mean? So this is what we call an orthogonal matrix. Okay. So J is an orthogonal matrix. And then we have some scaling going on. So determinant of J is equal to, as before, ux squared plus uy squared. So so J is equal to this square root ux squared plus uy squared times t, where t is orthogonal with determinant equal to 1, which means that it is in fact a composition of rotation and scaling, and it is conformal. Okay. So, in particular, f is conformal, has to preserve all these angles. Okay, so this ends the proof.
If we want this result, g equals to square root of this one, we don't need that the determinant is non-zero.
We need that the determinant is non-zero. Yeah, of course, I mean, we want to divide out by 0. Okay, so, I mean, if the determinant is 0, it means that, then you can sort of treat this case, it is a very trivial map if the determinant is 0, right? So if the determinant here is 0, it means that ux is 0 and ui is 0. So the function is constant. And then, is it conformal? Yes. Well, no. Well, yeah. Well, then it's not conformal. This is actually a good point here. So is a constant map conformal? So it sends everything to 2? Well, obviously not. So constant is not the same as the identity. The identity is clearly, this is a computer. So the identity is clearly conformal. But constant is not. It just sends everything to a point. Every curve, it has some angle. Every curve, we just go into a point. Okay? So all of this is true if the map is non-constant. Thank you. This is good.
I couldn't follow the argument. I mean, we have to say 2 arbitrary chords.
Yeah.
And to prove that the angle is preserved, but I don't see that there.
Yeah, so it is this condition. So preserving the angle means that for any 2 vectors, alpha, beta, and R2, then this ux, ui, ux, ui, so this is j. It means that j times alpha, j beta, divided by their norm, is equal to alpha beta divided by norm of beta. So this is what it means. Okay, so maybe you're asking about what I did in this argument. So how did I show here that it preserves angles? Is that your question? And the reason is that I showed that actually, if you satisfy Cauchy-Riemann, then you then this matrix here. How does this matrix act on any two vectors alpha and beta? Okay. So I showed that. So I want to show that this holds. But then I showed actually something about this matrix. I showed it was an orthogonal matrix. And so it means that this matrix is in fact, I'd say something stronger. I say that this matrix is in fact a composition of rotation and scaling. You know, it was of this form AB minus BA. So it's rotation and scaling. So it means that when I take two vectors like this, any two vectors like that, then what I do is maybe I make them longer and I rotate. So in particular, I preserve the angles. So I don't even need to check it. This is what I'm saying. Okay, so worth repeating, there's a very strong connection between being conformal, between satisfying the Cauchy-Riemann equation, and between being holomorphic.
And they are equivalent, holomorphism and conformal.
Yeah.
Conformality are same.
Yeah, so this was the question that
because if it's a function is conformal, then it's differentiable, and it means
Yeah.
that it is a tensor.
Yeah,
Conformality.
exactly. Yeah,
And
I guess that would be a proof. Yeah. Yeah. Yes.
this condition was right there
Mhm.
to prove that the function is conformal. The scalar product of GA, GB
Yeah,
is divided by V. We can just prove it for the case where we choose two linearly independent vectors, and we prove it only for two vectors, and it's all.
By some kind of.
Because G is linear, so we can, for example, the element of the E1 and E2, for example.
Yeah.
We prove it only for that it preserves this angle and orientation for only these two vectors.
Yeah.
Then it's preserved for all.
If you show a function is holomorphic, it's enough.
Yeah.
Yeah, that's also enough by the theorem. Yeah. Probably the simplest way of checking this in practice conformal is using the theorem and showing that Cauchy-Riemann is satisfied. But yeah, of course, you have a point. You can certainly do these things. Okay, I will erase also this. So now we will go into a second topic. So this was really showing that holomorphic maps are conformal and discussing this. But then there are other very fundamental maps in complex analysis that are conformal. Okay? So now we will jump into a slightly new perspective on all these things. So far we have studied holomorphic functions on the complex plane. Now we will study it on, so you're all studying topology, so now we will study it on the one-point compactification on C. It's called the extended complex plane, or the Riemann sphere. And then we will study, so once I introduce the Riemann sphere, we will study Möbius transforms, which is one of the most important examples of conformal maps in applications. Okay? So the Riemann sphere. So and rational functions. Okay, so you will recall that C is a metric space where you remember the metric was this, given by the absolute, using the absolute value, R2. But is it compact? Well, of course, it is not compact. Topologically, it's like R2, right? Topologically, it's exactly the same as the Euclidean plane, R2, which is not compact. So we will now very soon consider compactification. So let me just as motivation, let's give an example of further examples of analytic holomorphic using these synonyms functions. So now we have the following example that if F and G are analytic on some subset U C, it implies that f divided by g, is this analytic? Exactly, so it's analytic on u minus the zeros of g. So if we take away some points here, some zeros of g, then this is, in fact, so this is u. Then if we take away some few points, the zeros of g, then it is actually analytic on the open set that remains. So you remember holomorphicity is always an open set. So, but if we take away some few points here, they are always isolated points, then we still have an open set that is topologically organized, and we are still analytic on these sets. Okay? So, in particular, we have rational functions. So now if we take p and q to polynomials in complex coefficients, okay, so they are defined on all of C, then so this is analytic. So of course polynomials are holomorphic on their entire function. So they are analytic on C minus the zeros of Q. Okay, and moreover, if Q of A is equal to 0, then P of A over Q of A tends to plus infinity. So we assume that we have no common zeros, okay? So we have P and Q, no common zeros. And if we do have common zeros, we divide out by this factor, okay? So we assume we have no common zeros. When this is true, if we write it in its simplest possible form,
The modulus of this quotient.
Yeah, absolutely. Tends to infinity or something. Now, because what I want to do is I want to add one point at infinity, which represents both plus and minus infinity in some sense. So I did not have in my mind that it would matter. It just blows up in absolute value. So absolutely, this is what I mean. Of course, otherwise it doesn't make sense. So it blows up in absolute value. Okay, and what is important is that this limit exists. Okay, so this is kind of settled. This limit exists. It is not some strange behavior where as you approach this point, as z tends to a, so limit, I'm talking about the limit z tends to a of p of z over q of z, sort of it exists. So what this means is that I can actually extend this function to be continuous on the one-point compactification of this, you will see. So this will be sort of a motivation. So it is useful to consider rational functions, or in general quotients of any holomorphic functions, okay, as defined on this thing that I will call C hat, which is defined as C union a point at infinity. Okay? And in particular, I would then, in this case, send A to infinity. So, and this can be done so that it is continuous. Okay? So this is the one-point compactification. Can be done such that this extension P over Q from C hat to C hat is continuous. Okay, and this is important. So instead of viewing these rational functions as something problematic, we have this, what will be called a pole, as you will see later, that when you have zeros of Q, they blow up to infinity. Instead of seeing this as a problem, you can actually notice that it's still quite a nice function, and if you add a point at infinity here, then actually you can get a continuous function. Okay, so this will lead us to discussing the Riemann sphere. So I hope this will be clear in a moment why why all this is so good, so nice to consider. So this now leads us to the Riemann sphere. Okay, so the Riemann sphere is identified with this C hat, which is C where we have added one point at infinity. So topologically, the Riemann sphere is S2, which is the unit sphere in R3. Okay, so topologically it is this. So this is S2, and we will see how we identify this with C hat. Okay, so this is done via something called stereographic projection. So we have a projection here, which is from C, a one-to-one map, and what we will call the North Pole. Okay, N is the North Pole. This is where my family lives. Yeah, so let me draw this picture better. So what we consider is this unit sphere. Okay, so this is the point 0, 0, 1. So this sits inside these axes. This is x, this is y, this is z. Okay, this is the origin. And down here you have 0, 0, minus 1, okay, and so on. This is the unit ball of radius 1. And then in this xy plane, you identify it with C. So this is C, which is in the xy. We now identify with R2 as being the xy plane. Okay, so it goes, it doesn't look like it. This is a very hard picture, and I was never able to draw this picture very well. I mean, this thing goes straight through the ball, right? So the ball is half, so this is the plane, and the sphere here goes, the north hemisphere is above, and the south hemisphere is below. You cannot see it in this picture, but it doesn't, it's like, I don't know how to, how to draw this. Okay, let me just do this. Okay, so you have this thing, and then you have something called stereographic projection, which is defined in the following way. So this is a very important word. So the stereographic projection is a way to associate, so it's going to be a bijection from this sphere to the complex plane, which is now identified with C. And so it's going to be a bijection, from this sphere minus this point, the North Pole, to C. And then this North Pole, we will say that this is the one point that we add to compactify the whole thing. So this North Pole will be infinity. Okay? And how do we do this? So we do this in the following way. So let's say we have a point, Z, and we want to associate it to a unique point on the sphere. What do we do? Well, the idea of stereographic projection is that we look at this line here between Z and the North Pole. So you see, I'm somewhere here, and I have my sphere sitting here. The North Pole is here. So I take my line. At some point I will enter into the sphere, right, in order to go to the North Pole. So when I enter into the sphere, you agree with this, I have to cross into the sphere at some point, right? So when I cross into the sphere, I am here. And then I cross inside, sorry, this is terrible. I am here, and then I cross inside, and then I go to the North Pole. Okay? And this point here is a point on the surface of the ball, so on the sphere, which is this S2. So S2, of course, I mean, it's just the shell, it's not the inside of the ball. So this is a point x1, x2, x3. This is all sitting inside R3. Okay? So we want to associate Z to this point. So this is the idea. And of course, this is something that is bijective. This is very clear. I mean, if I take another point over here, or over here, then I will have this line, and it will cross into here somewhere, and I identify this W with this point here, which I will call. So I will call this image under stereographic projection S of W, and this is S of Z. Okay? So you can see that you do this thing, and the farther away you go, the closer you come to the North Pole, right? And for example, the origin here is already in the complex plane. This one is then, the South Pole. Yeah, so it's associated to the South Pole. Because you're not allowed to, it's the unique intersection of this line with the sphere not being the North Pole. Okay. So you have this bijection. Now this picture is already messy. So how it is defined? How is it defined? So I think it is very easy to understand when you draw the picture. Okay. So now we want to derive some formula for this. So what we want, so what I just said is this, that we want to send Z to x1, x2, x3. So send such that, so this is something in R3, and this is something in C. So such that the following is satisfied. So we know that this point should be on the same line as the North Pole. So we're looking at this x1, x2, x3 minus the North Pole. So this is the line segment here. Okay. This should be a multiple of this. So this Z here is identified in coordinates here. It's x, y, 0. Okay. So it's x, y, 0 minus the North Pole. Okay, for some lambda. So you're with me on this. So that this vector here is a multiple of this line here. This means that they lie on the same line between Z and the North Pole. Okay, so we want this to happen. Then we also want to say that x1, x2, x3 is not any point on this line, but it has to be the unique point on the sphere. So this means that being on the sphere means that the absolute value is 1, okay, of this x1, x2, x3. And then we tell you how you identify this complex Z with the coordinates x and y. And we do it in this completely standard way using x plus iy. So you have these things. Okay, and then we can solve the system. So we can solve the system to get some formula for this. So this means that so if you now look at this, you see that, what does it say? So it says that x1, so we will solve the following system. So x1 is equal to lambda x, okay? So x1 is equal to lambda x. x2 is equal to lambda y. And x3 minus 1 is equal to lambda. So we solve this system. So, and of course, so this is correct, right? What was correct? So minus 1? Yeah, because
yes, equal minus 1.
Is equal to minus lambda. Thank you. Very good. Equal to minus lambda. So what you want to do, so where we have some condition that all these points lie in the sphere. So then the second condition, it becomes that lambda x squared plus lambda y squared plus so x3 squared, so plus 1 minus lambda squared is equal to 1. Okay? And this, so this is lambda squared times x squared plus y squared. And x squared plus y squared is the absolute value of z squared. So this is lambda squared, absolute value of z squared, plus lambda squared. So then we just have this. So this is lambda squared minus 2 lambda, and then it is minus 1 plus 1, and there is a 1 here. Sorry, plus 1, yeah, so sorry, plus 1, and then these cancel, so it is equal to 0. And now, so this means that if we take out now lambda, we can write it like this. So lambda times modulus z squared plus 1 minus 2 is equal to 0. Okay, so it's just factorization. So now let's analyze the solutions to this. Okay, so what does it mean? So the first possibility, if you look at this, is that lambda, so lambda is multiplied by all of this. So the first possibility is lambda is equal to 0. Okay, so what would it mean that lambda is equal to 0? It would mean that x1, x2, x3 is equal to 0, 0, 1. Is that what you said? Yeah. It's equal to 0, 0, 1. And, okay, so what does this mean? So this means that we are in the North Pole. So this corresponds to the point at infinity in some sense, okay? And then lambda not equal to 0 is the proper case. Okay, so that means that lambda, so this thing is 0, okay? So it means that lambda is equal to 2 divided by 1 plus module of z squared. Okay, because that thing is 0. And so, then we want to write down a formula for x1, x2, x3, and it will be then equal to, so x1 is lambda x, where lambda is equal to 2 divided by this. So it is equal to 2x divided by 1 plus modulus z squared. It's equal to 2y divided by 1 plus modulus z squared. And then it is equal to the following. Okay, because x3 was equal to 1 minus lambda, and 1 minus this is equal to this. Okay? So, so this is the formula for x1, x2, x3, and z is equal to the following. You can see that z is equal to the following. Okay, so this is the correspondence. So if you start with z equals x plus iy in the plane, and you associate z with this x1, x2, x3 on the sphere, then x1, x2, x3 is written like this in terms of the coordinates for z, where z is equal to x plus iy. And if you're given the coordinates on the sphere, then you can see that it comes from z equals x1 plus I x2 divided by this. Okay?
How do we get this?
And how do we get this? So we see that z, we identify z with xy 0 in the plane, right? So now if we are in R3, so we want it to be in the xy plane, so the last coordinate is 0. So this is x and y. And x was equal to, so lambda x was equal to x1. So x is equal to x1 over lambda, and lambda was equal to 1 minus x3. So this is equal to x1 over 1 minus x3. And y is equal to x2 over 1 minus x3. So this point here is x1 over 1 minus x3, x2 over 1 minus x3, and 0. And if we now identify this back, this corresponds to x1 over 1 minus x3 plus I times the second coordinate, x2 over 1 minus x3. So therefore we get this formula. Is that clear? I know, I mean, you cannot maybe see what is even written here. It looks very messy, but if you heard my explanation. So it's this identification. So x plus iy we identify inside R3 with the point xy 0. Okay. So we have these formulas.
And there are also the points inside of the sphere.
Sorry?
What about the inside of the points the sphere?
The points that are inside. Yeah, so the points that are inside, what will happen to them? So you see, so my drawings are so bad that I think it's better to imagine it in our heads. So you see the sphere, this plane cuts through the middle of the sphere. Okay? So if you're inside, you're inside somewhere here, maybe not exactly on the z-axis. So you're inside, then you take the line up to the North Pole. Now you have not yet crossed the sphere. But then on the other side, somewhere here, it will go out of the sphere, and you associate this point on the sphere to the ones that are inside.
I think this formula is different in this side.
No, this formula should always be true, no?
Because this only depends on x1, x2.
No, x3.
X3. X3 is here.
No, inside also.
What do you mean? Okay, so yeah. Do you want to? I'm not sure I understand. Maybe if I continue explaining, we'll see if it helps, and otherwise ask again.
It is same in the inside of the point of the sphere.
Sorry?
And it is this formula is same for the points that are located inside of the sphere.
Yes. Okay. So let's try doing this. So the intersection. This is a complex plane, and if we now say that the sphere goes like this and then continues on the other side of the blackboard, then it intersects the surface like this in a circle. And if you take some point inside here, is this what you mean? Yeah. So then you have the North Pole lying here.
Yeah.
Okay, outside of the table. So you take the line from here to the North Pole, and then you continue on the other side of the blackboard, right? And you continue, and then you will exit the sphere on the other side, somewhere on the southern hemisphere. You will exit the sphere, and this is the point that you associate to Z inside the sphere.
Yes, but this different.
Okay, you have a problem with this formula.
Because it is, I think it's not depend on x3. Because we can take x1 and x2.
So this is if you have this point x1, x2, x3 on the, so it will be somewhere on the southern hemisphere. Then this should associate some z which lies inside this unit disk.
Because the x1 and x2 is same for the.
Ah, okay. So you mean that there is for every point there is.
Same.
So you have x1, x2, x3, and x1, x2 minus x3. Is this
x1 and x2 of the sphere is same for z.
Yeah.
So I think that there are z only equal to x1 plus e x2. Yes, in the inside.
You say x3 depends on x1 and x2?
No.
It depends.
I tell you after.
Okay, we continue this discussion after the lecture. I mean, this formula is always true, but we will try to see how we can explain it. Okay, so let's make this remark. So if z is somewhere on this, so this is the unit circle now, okay? So this is one. So if z is somewhere on the unit circle, then this corresponds to x3. being 0. So then you associate something which is still on the intersection point. So now if z is the absolute value of z is greater than 1, so you're very far away, then you will associate something which is on the northern hemisphere, right? So then x3 is greater than 0, and if you're here on the inside of the circle, then you associate something on the southern hemisphere, so x3 is less than 0. Okay, and then what we want to do is that we want to compactify this space. So now we have identified C. So we have identified C minus C with this sphere minus a point. So now we can identify, so this corresponds to infinity, and this S2 minus n corresponds to C. Okay? So this gives an identification between this C hat, which is C union this point at infinity, and S2, which is the Riemann sphere. And by the way, an exercise, which I very much like, is that S2 is so, and all of these things is exactly CP1, so this is the complex projected, so this is a bit outside of the course, but this is the complex projected line. You know what this is. So this is C2 minus 0, where you identify x with lambda x for lambda in C star. So this is a complex manifold, a simple one. Projected manifolds are very important, so this is one of the most used examples. And this is actually a sphere. I feel that this is something that I wanted to tell you because a lot of people, I ask them, even after the diploma course, what is CP1? Can you draw it on the board? And I want them to draw a sphere, but nobody draws a sphere. So, somebody asks you to draw CP1, draw a sphere in R3. And you should think about what? Okay, so let me continue here. So we have this stereographic projection, what's the name of this map. The stereographic projection associates Z to a point in the extended plane, so on S2, minus that. So is it clear what stereographic projection is? So stereographic projection, let me just write it again. So this is the map that takes Z plus X plus IY into this whole thing that I wrote, 2x over 1 plus z squared, 2y over 1 plus z squared, and whatever the last one was. I guess I put it somewhere. Does someone remember without us having to recompute the thing? Z squared minus 1. Yeah. Yeah. So this is the map we call stereographic projection. And this is the image, which I will often denote by S of Z. Okay? And this map has an inverse, and the inverse was given in that way. It maps x1, x2, x3 to Z, which is x1 plus yx2 over 1 minus x3. This is the inverse stereographic projection. So now it is clear what we are talking about. Okay, and now so I want to mention to you a metric. So now that we identify this infinite complex plane with a sphere, which is something compact, then we have to take care, how do we treat this as a metric space? Because, on the sphere here we have so in the plane, of course, the distances can become infinitely large, but now we want to treat it as something compact, where the distances stay bounded. So we can define a new metric, or a distance, in C. So we can define a new metric in C by using the Euclidean distance in R3. Okay, so we say that, so this is called the chordal distance, and I will denote it like this. So I will write that. So this is the chordal distance. Chord, because you know a chord is like a rope, and this rope is like you take stereographic projection, and you take the rope, the chord between Z and the North Pole, and you look where the point of intersection. I think it comes from here. Okay, whatever. It has to have some name. So the distance between 2 points now in C, so ZW in C, is defined as the Euclidean distance in R3. So this is important, in R3 between S of Z and S of W. Okay? So what I do, I have 2 points, I associate their corresponding points on the sphere, and then I look at the Euclidean distance between them. So of course this distance cannot be very large, right? It does not go up to infinity. So now it is something compact. But this is a distance. So you can check that this is a distance. And then we have an exercise, which is on the exercise sheet that I will give you today, the second exercise sheet. It's messy. So, okay, so we have the following exercise. That you have the following formula for the chordal distance. So the definition is what I just wrote, but there is a convenient formula, and it is equal to this. That's a 2 times the absolute value of Z minus W. And these absolute values, this is of course now distance in R3, okay? Euclidean distance in R3. Sorry. Yeah, sorry. R3, R2, it's the same. That was stupid. Yeah. It's an R2. Okay. And then we have the following theorem, which I want to state. So really, you want to think about what happens. So you have this sphere, and then you have a plane. Okay. And by the way, a small remark. So I define this to be the sphere where the plane cuts through the middle, through the equator. But for example, when I was taught complex analysis, I was actually taught that this plane sits on top of the sphere. So the south pole barely touches the sphere. These are 2 competing conventions, depending on who is your professor, what country you are in, and so on. You may learn it differently. The formulas then may differ by a half or something like that, some stupid factor when you give your formula. So just be consistent when you work, define it in whichever way you want. The theory is exactly the same. It's just if you want to sit it on top or if you want the plane to go in the middle, you get the same thing. So I was taught it sits on top, but now I prefer it to go through the middle. So yeah. Anyway, now we see these points. Let's look at how it behaves. If you take a circle here. So, okay, maybe let me write the theorem, and then you will see. So, stereographic projection is conformal. Okay, and not only is it conformal, but it actually sends. So, I mean, the theorem is this: it is conformal. But on top of it, I want you to remark something. That if you take a circle here, so this is the North Pole. So if you take now a circle on the sphere is something that goes all the way around the surface of the sphere, a line. Then what is the image of this circle?
A line or a circle? Yeah. If it's vertical.
Exactly, but now exactly this one that I drew.
A line.
It is a line, yeah. So you see we start here, we start very close to the North Pole, and then we cut the sphere somewhere, and then it has to be a point very far away. We just touch, it's very far away. Then, as we go along, it will come closer and closer, and then it will go out the other way. It will be a line in C. So the image of this thing would be some line going out in C like this. if I instead take a circle like this one, then of course, I go from here, I cut somewhere, and then I cut here, and then it is the circle. Or if, maybe it's a circle here, I cut here, and it becomes a bigger circle in the image of the sphere. Okay? And of course, I can also have things that go on the side like this, but also this will be a circle.
Yeah. Only circles passing through N.
Only circles passing through the North Pole become lines. Exactly. All the other ones become circles. So maps circles in the extended plane to lines or circles in C. This is very important observation. Okay, and the fact that it is conformal, that this thing preserves angles. So I will not write down a proof of this. But if you look at the picture, it is not too hard to believe it. So let's say that you have. Sorry?
It's hard to believe.
It is hard to believe?
No, it's not hard to believe.
Yeah, and? Yeah, it's not hard to believe. Well, what I'm saying is I'm leaving this for you, to do. And I will prove a similar theorem later. So,
if the one, is all those circles centered in the center of the surface? Or it's not necessarily?
no, not necessarily.
Okay, then the one that had a slope that is, it's not vertical or horizontal.
Yeah.
And if all of the circle is above the surface, the plane, why is it a circle? Why it is a circle?
Yeah. So you'd have to. So this is part of the exercise, the sort of understanding. So actually, this is also part of the exercise sheet. But so you will try to understand this, and you have to draw figures. You have to understand a lot of things. The proof is honestly a little bit messy, but yeah, nothing. It's obvious if it's horizontal and parallel. If it's like this, then
it looks like
it looks like maybe an ellipse.
It will go farther.
Yeah.
And the points that is near the plane will be near to the center, so it will be.
Yeah.
It's
It's
not centered.
not centered. That is why. Yeah. But yeah. So I'm leaving this as an exercise anyway. So try to understand it, and at the very latest. So the way the course works is that I prove many things. Sometimes I leave things as an exercise for you to think about, and if you don't understand it after thinking about it, then of course it's very important that at some point we provide you the opportunity to discuss it and learn it. And this you can either do with me, but also in the tutorials with Fernando. So you haven't had your first tutorial yet, but the function of this tutorial is precisely this, right? That you don't understand some exercise fully, Fernando will explain to you. So for example, this exercise, you have also this time to discuss why is this circles. I thought about it for 5 days, still don't understand why this has to be a circle.
And
Please enlighten.
it's a plane pass through the middle of the sphere.
Yeah?
And this map again preserves the circles. Yes.
So the plane passes through the middle of the sphere? Yeah, that's how I think about it now.
It's not there.
Sorry?
If the plane pass through the middle of the sphere.
Yeah.
Middle of the sphere.
You mean for the definition of stereographic projection? Yeah, this is how I defined it now actually.
Yes.
Yeah.
It is still preserve the circles.
So it must be.
Yeah, it still does. Yeah, still should. Okay. Well, I have to stop here. Anyway, so let's stop.